So I found something really cool and I wanted to share it with you. This may be interesting if you just like MTHFR in genetics and biochemistry, or if you have a child or yourself with autism or ADHD or depression, anxiety, lack of motivation. It all correlates. Okay, you need folate to get into your brain. Your folate is responsible for making your neurotransmitters. It's converted into this thing called BH4 or biopterin, but it's also responsible for making this stuff called S-adenosylmethionine or SAM, which is needed, it's required to degrade neurotransmitters. So this would apply for things like anxiety and like even schizophrenia too. Now, there's been a debate on how folate gets into the brain because the brain is privileged. It has cerebrospinal fluid. It has its own fluid, partially to protect the brain from anything that could be in the blood that would be detrimental, right? There are these cells called choroid plexus cells, and they form kind of like the barrier, the lining between the blood and the CSF. So we've been trying to figure out how folate gets across this barrier. And in the past, we thought that it was a two-part system. So we thought that there was this protein called folate receptor alpha, and there was this transporter called PCFT, or proton-coupled folate transporter. And everybody just kind of thought that PCFT was a backup to this system. So if the folate receptor alpha did not work, which very frequently happens, folic acid will destroy it. You can make antibodies to the folate receptor alpha. Sometimes these are induced by consuming dairy, or sometimes people just have like gene mutations in folate receptor alpha and it doesn't work really well, right? So folate receptor alpha is your main folate transporter in your brain. We thought that PCFT was kind of the backup. So if the folate receptor alpha was not working for various reasons, then PCFT would kind of like step up and do the job, right? But I noticed that PCFT only functions in very acidic conditions. We're talking like it really loves to do its job at a pH of like 5.5, and your blood stays very, very tightly regulated around 7.4. They can get down to like 7.3 and up to maybe 7.45-ish. Somebody correct me in the comments. But there's no way your blood is getting to a 5.5. We would have major issues, right? So there's no way that PCFT is the backup for folate receptor alpha because it genuinely cannot work in neutral conditions, 7.4. So I started digging a little bit because I'm one of those biochemists that I don't accept those like little mystery black boxes of science. I want to know everything. So what typically happens when you're working on folate receptor alpha, when that's the main guy, is that it's a receptor, it's not a transporter. So it's kind of like a cup on the outside of your cell's surface, whereas transporters are like a tunnel. So folate will bind to the little cup on the outside, and then the whole thing, the cup and the folate get internalized. So your cell membrane is going to kind of like bend inwards. It's eventually going to get pinched off into these little tiny bubbles called endosomes. Now, folate receptor alpha has to like let go of the folate, right? It's not going to be useful if it stays bound to folate the entire time. And I don't know if you know this, but we're essentially little organic machines. So the really cool thing that happens is this little bubble, this endosome, gets really acidic. And that change in pH is going to pop that folate right off that folate receptor alpha. Now, as a fun side note, folic acid is a synthetic compound. Your brain cells cannot get these little bubbles acidic enough to pop folic acid off of folate receptor alpha. So you actually end up having to destroy the entire folate receptor because typically these get recycled back to the outside membrane so they can do the same job again with the same protein. But with folic acid, that doesn't happen. Because it genuinely can't let go of the folate, your body has to just literally destroy the entire thing and remake it from scratch. But these little bubbles, after folate pops off of the folate receptor, they don't get unacidified. They stay acidified. And this is where PCFT comes into play. PCFT has to transport folate with acid. So it actually will pump acid out with the folate, and that's how it works. It can't get around this. That's literally just how the machine works. So PCFT is on the outside of the cell's membrane. Yes, because it gets pinched in when the bubble is made. So that way it is already there to where when that little bubble, that endosome gets acidified, right? folate pops off of the folate receptor, PCFT is there to pump folate out of that bubble, out of that endosome, into the interior of the cell, which I think is so cool. And I'm really surprised that nobody there are studies about it, obviously, because that's where I found my data. But I'm really surprised that so many people are still thinking that PCFT is your backup to folate receptor alpha on the outside of the cell, because it genuinely won't work. Now, the really cool thing is if folate receptor alpha is down, right? You've got antibodies to it, you've just been consuming a lot of folic acid, and your DHFR enzyme is busted. You have a gene mutation to where folate receptor alpha just doesn't work just normally, right? There has to be a backup mechanism for this. And previously, people thought it was PCFT. But the thing is, PCFT actually prefers to transport folic acid over methylfolate. And we've noticed that if we give people high doses of folic acid, they're not really improving their brain and cognitive abilities because it doesn't work, right? We see no improvement of symptoms. But when we give them methylfolate, or when we give them folinic acid, which is a little bit safer, it's a high dose, and I can explain that later if you would like me to, their symptoms actually do improve, especially if you keep these people at an ungodly high level of methylfolate or folinic acid in their blood. That's called substrate push. We use it all the time. And I can also explain substrate push to you if you would like me to. Now, do you know what functions at a normal pH that prefers methylfolate, that likes it better than folic acid? The reduced folate carrier. And this is really cool because it is present on the outside of these choroid plexus brain cells. It's just in really, really low concentrations, which, fair, you wouldn't need it to be in high concentrations because of the fact that typically folate receptor alpha is doing all of the work. Folate receptor alpha is what's called a high affinity, high transport. So it can move a lot of folate really quickly, and it really likes folate. So it's going to grab it really fast. Kind of like when I give my kids candy, right? They really love it and they can eat a lot really fast. The reduced folate carrier isn't as, it doesn't like folate as much. It has a lower affinity, kind of like my kids in vegetables, and it transports it a little bit more slowly. Now, this is a really cool part. So I was looking at studies and I was trying to figure out, okay, if folate receptor alpha is broken, does the number and the amount of the reduced folate carrier, RFC, increase? And it does. The only problem is that it takes about 12 hours for you to make more RFC mRNA, so to start the process, right? And it could take up to 2 to 4 days for you to start making and having the actual proteins in a decent amount of concentration to do any work. So that being said, if you're taking methylfolate to try to improve brain function, genuinely give it 4 days. The other thing that sucks about this is that the reduced folate carrier increases because your brain folate levels are low. So it's in response to a deficiency. There is no mechanism in your brain to where your brain can stop and think, oh, I am getting all of this folate due to the reduced folate carrier, so I need to keep making it, right? Even when my brain levels are normal. You see where I'm going with this? So once the reduced folate carrier does its job and your brain levels return to normal, all of those signals that your body has to increase the amount of the reduced folate carrier on the outside of your brain cells, they're going to go away. Which means that you are going to be deficient, right? Because something happened to folate receptor alpha, a high dose of folic acid, you develop antibodies, whatever, right? And then your brain is going to upregulate the reduced folate carrier, and then you're going to become sufficient. You're going to feel good. Your brain is going to work. Until when you become sufficient, your body is going to stop producing as much reduced folate carrier. So you're going to fall into deficiency again. So it may be like a back and forth seesaw between deficiency and sufficiency, especially if you continue to consume folic acid or you just have a gene mutation on the reduced folate carrier, right? But I thought this was really cool and wanted to share just the edge of science with you guys.